In previous videos we've seen how to find the determinant of a 2 by 2 matrix. We've also seen the role that the determinant plays in solving simultaneous linear equations and in finding the inverse of a matrix. Now what we're going to do in this video is we're going to look at 3 by 3 determinants of square matrices with 3 rows and 3 columns. Now if you can remember, the rule for 2 by 2 determinants was very straightforward, but perhaps not very intuitively obvious. With 3 by 3 matrices it gets a little bit more complicated and again not very intuitively obvious. And to work out the determinant of 3 by 3 matrices we need to first of all introduce some other ideas called minors and cofactors. And we'll start by doing that, and throughout this video we'll always use the same matrix A. So this is the matrix A that we're going to use, and you can see that it's got 3 rows and 3 columns. We can only find determinants when we have a square matrix, a matrix that has the same number of rows as it has columns. And to find the determinant of this 3 by 3 matrix, we first of all need to understand what's meant by a minor. Every element within our matrix has its own minor. So we spell minor like this, M-I-N-O-R. And the minor of an element is the value of the determinant we get when we cross out the row and the column containing the element we're looking at. So let's look at this element 7. This element 7 is in the first row and the first column. So if we cross out that row and that column, I'm going to hide them rather than cross them out. You see that we're left with a 2 by 2 matrix, and we can find the determinant of that 2 by 2 matrix. So the minor of the element 7 in matrix A is this 2 by 2 determinant with entries 3, -1, 4 and -2. Remember, the rule for evaluating a 2 by 2 determinant is to multiply the 2 elements on the leading diagonal and then subtract the product of the 2 elements that aren't on the leading diagonal. So we do 3 times -2, and then we take away 4 times -1. So that gives us -6 minus -4, which is -6 plus 4, which gives us -2. So the minor of our element 7 from our original 3 by 3 matrix is the value -2. Now we can do the same thing for any element in the matrix and find its minor. So let's pick this 4, the 4 that's in the third row and the second column. And we're going to find the minor of 4. So we go through the same process. The 4 is in the bottom row, so we cross that out, and it was in the second column, so we cross that out. And so we see we're left with a 2 by 2 matrix. And so we work out the determinant of that 2 by 2 matrix. Here's our 2 by 2 matrix, 7, 1, 0, -1. So we do 7 times -1, which is -7. And then we take away 0 times 1. So we're taking away 0, and so we're getting an answer of -7. So the minor of the element 4 in this matrix is -7. Now we could, but I'm not going to now, we could work out the minor of every single element in our matrix A, and we'd get a value of the minor. So we get 9 values, 1 for each element of the matrix A. Now I hope you can see now what the process is to work those out. I want to go on now from minors to cofactors. And to get from minors to cofactors, I need the idea of what we call a place sign. Every place within the matrix has a sign associated with it. We always start with a plus in the top left-hand corner, and then we alternate the signs. So So as we go across the row, we're going to go plus, minus, plus. And as we go down the column, we're going to go plus, minus, plus. And I hope you can see that if we fill this in, it will look like this. So this is the matrix of place signs. So for instance, the element 4 we've looked at before has a place sign of minus, whereas the 7 that we've looked at has a place sign of plus. And we use the place signs to convert minors into what we call cofactors. So the cofactor of the element 7 is equal to the place sign times the minor. And that's true for all the elements. Every element has a cofactor which we find by doing the product of its place sign with the value of its minor. So for the element 7, the place sign was plus, and for the element 7, the minor was minus 2. So we get plus minus 2, which is just equal to minus 2. So the cofactor of the element 7 in this matrix A is minus 2. And if we take the element 4, the cofactor of 4 is equal to its place sign times its minor. So the minor of 4 we saw was minus 7. The place sign is a minus. So we want place sign minus times the value of the minor, minus 7. So minus minus 7 is plus 7. So the cofactor of element 4 in this matrix is 7. We're now going to calculate the determinant of our matrix A by using the cofactors. So if we look at what we've written down here, what I've done is I've taken our matrix A and I've worked out the 9 minors. So the minor of 7 we've already seen is minus 2, and the minor of 4 we've seen as minus 7. And I've worked out all the other minors and I've put them into this matrix here that I've called M. Now remember that we have a place sign matrix that starts with a plus in the top left hand corner and alternates sign as you go down or across. And then we calculate the cofactors by taking the minor and multiplying by its place sign. So I've assembled into the matrix C the cofactors of all the elements of our matrix A. You can see that you get the cofactors from the minors simply by multiplying by the place sign. Now, to work out the determinant of A, what we have to do is we can pick any row or any column. So let's say we were to pick the first row. You can see that the row has 3 elements in it. If we'd picked a column, that would have had 3 elements in it as well. What we do is we pick our row, we've got 3 elements, and they've each got their own cofactor. So what we're going to do is we're going to form the product of the element times its cofactor. So we'll be doing 7 times minus 2, 2 times 3, and 1 times 9. I've just explained what the steps are for calculating the determinant, so let's now write it all down. We've seen that the only things that really matter are the matrix we started with and its cofactors. So that's all we've got on the sheet. So here's our matrix A, and here's the matrix of cofactors. Now remember, what we need to do is we were picking the first row. We could pick any row or column, but we've chosen to pick the first row. And to work out the determinant of A, we write DET for determinant, DET brackets A meaning the determinant of A, and sometimes you'll see this written with vertical lines to mean the determinant of A. And what we do, because we've chosen the first row, we write down the elements of the row, 7, 2 and 1, and we multiply each element by its cofactor. So we're going to do 7 times minus 2, we're going to do 2 times 3, and we're going to do 1 times 9. So we're going to get these 3 products and then we add them up. So 7 times minus 2 is minus 14, 2 times 3 is 6, and 1 times 9 is 9. So when we work out minus 14 plus 6 plus 9, we get the answer 1. So the determinant of A is equal to 1. Now you're probably thinking, well, what if I'd chosen a different row or a different column? Surely I would have got a different answer. So let's choose a different row, a different column, see what happens. Let's choose the second column. So if we're going to use the second column to work out the determinant of A, we've got elements 2, 3 and 4. 2, 3 and 4. And we multiply these by their cofactors. 2 gets multiplied by 3, 3 gets multiplied by minus 11, and 4 gets multiplied by 7. So we get the three products and we add them up. So 2 times 3 is 6, 3 times minus 11 is minus 33, and 4 times 7 is 28. When we work this out, we get 1. So we get the same value. And we'll always get the same value whichever row or column that we choose to use. It doesn't matter, it's completely our choice. So what this means is that if we're working out the determinant of a matrix, we actually don't need to work out all 9 cofactors. You see, when we used the first row, we only needed these 3 cofactors. When we used the second column, we only needed those 3 cofactors. So before we go ahead and work out all 9, if all we want to do is work out the determinant of A, we should decide which row or column we're going to use first, and then only work out the cofactors that correspond to the row or the column that we've chosen. And in general, it's a handy idea, or a good idea to keep your workload down, is if you've got zeros in a row or a column, that's a good row or column to choose, because you don't need to actually work out the cofactor that goes with the 0 element, because it's going to end up being multiplied by that 0 element. So if we use the first column, the first value is 7, the next value is 0, and the last value is minus 3. And we then have to multiply these elements by their corresponding cofactors. 7 times minus 2, 0 times 8, and 3 times minus 5. Add them up. So we get 7 times minus 2 is minus 14, 0 times 8 is 0, minus 3 times minus 5 is plus 15. And minus 14 plus 0 plus 15 is equal to 1. The same answer as before. Well, we knew it was going to come out to be the same answer as before. The important thing is that we really didn't need to know what the cofactor of 0 was. So once we'd chosen to use this column, we actually only need to find the cofactors of 7 and minus 3, because the cofactor of 0 is going to get multiplied by 0. So what we've seen then is how to work out the determinant of a 3 by 3 matrix. What we do is we pick a row or a column, and to keep our work as low as possible, we choose the row or column with the most zeros. And then what we do is we work out the cofactors of every element in the row or column that we've chosen. But we don't have to work out the cofactors of the 0 elements, because what we do then is we multiply each element by its cofactor, and then we add up the products of element times cofactor. And that's how we work out the determinant. Now this process works for any size square matrix, although once you get above 3, the amount of arithmetic involved gets to be very large.